Hi everyone, and welcome to the video on section 6.1. In this video we're going to be doing area between curves. So let's get started. The area between curves is usually easier to do by just kind of thinking through a picture, especially of the scenario you have. We're always going to start with a picture. So what are we trying to do here? We're trying to find this blue shaded area. Okay, area under something, our first thought should be integral. So, okay, let's just start off with this. So what is that going to give us? Let's shade that. That's going to give us this shaded region here. And then it extends, because remember, the area, right, the area under this curve, F, goes all the way to the x-axis. So okay, that's pretty good, but unfortunately we overdid things a little bit right here, and we missed this chunk. Okay, so then how are we going to get the area, the rest of the area? Well, we could try something similar. We could do the integral from a to b, of g of x. What's that going to do? Well, that's going to pick up this. So that's looking pretty good. And then what it's going to do is right at this point here where g crosses, it's now going to pick up this. Okay. So we just have to think through and make sure we can figure out kind of how to put these two together so that I get this plus a positive this, and these two cancel. All right, so what we have to do is kind of think through what's going to happen right here. So in this little area here, remember what happens when I integrate from A to this point, which we're going to label this intersection point with the x-axis here where we cross over. We're going to call that C. So when I integrate from A to C, g of x dx, okay, when I do this integral, I'm going to get a negative number. Remember, if I do this integral from a to c, but my function's down here, I get a negative number. And remember, when we were talking about area, what did we have to do? We had to hit this with a negative, right, in order to actually get it to be a positive number to talk about area. So somehow I need to set this up so that when I do my integral of g, when I'm going from a to c here, I need to have hit this with a negative so that it can flip to be a positive number. Okay, so how can I do that by combining these two? Well, one thing I could try would be to just do this, right? Because if I put a minus out there, look, I got a minus in front of the g integral. So it's okay, maybe that works. But what we have to do here is think about this piece now. Again, this integral is the black shaded, the whole black shaded piece, and I've overcounted a little. Okay, now this chunk of this integral, of the green, what's going to happen there? From C to B, my function's above the axis, right? So that integral will be positive. It'll be me actually talking about the real area here. But the idea is I don't want to count that, right? I already counted it accidentally with this integral, so I somehow need to take it away. Oh, I subtracted. Well, look at that. The subtraction actually does double duty here. The subtraction sign takes this integral from a to c, which would be negative, and flips it to positive. Awesome. And what it does here is it takes this positive value, and because I put a minus in front, makes it negative so that this just little chunk in here with green and black will cancel, and I'll be left with the blue. So there you go. So that's kind of how you can think through something like this, like how this works, is draw a picture and try to see if you can kind of put together the idea. But that's it. We just do the integral of the top minus the integral of the bottom, or if it's easier, depending on your scenario and your functions, Of course, you can rewrite this as the integral from a to b of f of x minus g of x as one integral. But often we like separating because it's just easier to do it that way. But either way, this works. All right. So you can go down here and think through the description of this, which actually thinking through this is going to be helpful for the volume section because it may not be super clear when we do volumes how we do this process of trying to fill with rectangles, and sum up rectangles as you let the width get smaller, like we've defined for an integral. It's not like necessarily a super straightforward jump to volumes, how this process works. So this is a good reminder for yourself of, when we do the integral, like what were we actually doing? We're trying to fill up rectangles, right, as an approximation, and then we realized, the more rectangles, making them thinner each time, that's a better approximation. Take that limit, and you get the integral. So it's a good thing to remind yourself of. Okay, so we've got our formula. So how do we do a problem with this? So here's a problem. Y equals log x, xy equals 4, x equals 1 to x equals 3. So it's very, very important for you to try and draw this out. Very important. Why do you want to do that? Well, let's kind of go through the list of things that you need to do. So let's just write the formula here. A to b f of x minus g of x dx. Okay, so what do I need to know? Well, things I need to know. Need to know. What do I need to know? I need to know a and b. Okay. Usually that's just given in the prompt. Not always, though. All right, what else? I need to know what's f of x going to be and g of x, aka, right, which function is top and which one's on bottom. That's very important as well. I got to know which one is on top because that goes first, and then subtract the one that's on bottom. I got to figure that out. A graph is a very nice way to help do that. All right? And then once I have those things, I can plug into the formula. So this is actually going to take a little algebra here because we actually want a function. So this is y equals 4 over x, right? As long as, of course, x is not 0. Which, when we go here, yep, we're between 1 and 3, so we're good here. We can rewrite things in this form. So this should be the integral 1 to 3. Okay, 1 to 3. All right, so you can even kind of draw a little here. So I want this area in between of f of x. Okay, now we got to think about this. Which one of these is on top, right? Is it 4 over x is on top, or is it log? Well, this is a little tough to kind of look at, and this picture is a little deceiving, right? Because this isn't actually 0. If we're looking at the way this works, this is 0.5. So this is log, because as I get bigger, log gets bigger. This is 4 over x, because as x gets bigger, this gets smaller. So this one is 4 over x. This one is a log x. And so that means I should do 4 over x minus log x dx. There we go. Okay. So not too bad of a setup, right? So, okay, how do we do this then? Well, we've got to do the antiderivatives here. So we could separate this if it's easier to see piece by piece, since we've still just kind of really started doing this process with these different functions. All right, so antiderivative here. We can move the 4 out, right? We could take that 4 out. That makes it nicer. And then the antiderivative here is 4 natural log of x. No absolute values needed here because 1 to 3. All these are positive. Log will be positive as soon as you're 1 or bigger. Well, it'll be 0 at 1, but as soon as you're bigger than 1, it'll be positive. So that's good. And then 1 to 3. This one's much trickier. This is an integration by parts, one of those tricky ones, right? Where u is ln x, du is 1 over x, dv is 1, v is x. So definitely one of those tricky ones to kind of go through. But what you're going to end up getting is minus x ln x minus x. And then that'll go from 1 to 3. Okay, so all we have to do is just plug in the bounds now, which isn't too bad. So that's going to be equal to, I'm just going to do all the 3's first and then the 1's after. So this is going to be 4 log 3. Okay, now plug in the 3 here, minus 3 log 3. Okay, and then this transfers to a plus 3, minus minus. Okay, and that's minus, now plug the 1 in. Well, log 1 is 0, so 0. Okay, minus, plug 1 in here. Well, again, 0. Because log 1 is 0. 1 times 0 is 0. And then we get a minus, right, 1. So then altogether, that's 4 copies of log 3 minus 3 copies of log 3 is log 1 plus 3. Transfer. I know there's a lot of minuses here, right? But we got to transfer this over. So we ended up with minus. So plugging the 1 in, we first put a big minus. Then we plugged the 1 in here and got 0. Then we put the minus sign. Then we plugged the 1 in here, 0, minus 1. So minus, 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 that all becomes just negative 1. 3 minus 1 is 2. And we did it. Boom. So hopefully not too bad. All right, next one. So in this one, we are not actually given any bounds. What that implies, so if you're given this situation with no bounds, right? No bounds here, then that means that the two functions must intersect. So to find the bounds, you have to just figure out where the functions intersect each other. So we need to set these equal to each other. X squared equals 4x minus x squared. I'll just move this over and I'll get 0 equals 4x minus 2x squared. I'm going to do a little factoring. Take a 2 out, take an x out. That'll leave a 2 here, minus x. So then x equals 0 and x equals 2 are going to be where these intersect. Okay, so we found our a and b. Not too bad. So we got to figure out which function is which. So, we could just look at the picture here, and we see that the parabola that's opening up is on bottom. The parabola that's, because of the negative, is open down, is on top. Or one way you could do this is, if these two functions only meet twice, like they do, then you could just test a point in between. Plug one into this and this, each of these, and then whichever number you get out that's bigger, that's top. Whichever smaller, that's the one on bottom. But a graph is nice too. Okay, so we now have the top and bottom. We now have the bounds. We can set this up. So we're going to end up getting the area is equal to the integral from 0 to 2, and then the top function, 4x minus x squared, minus the bottom function, dx. Okay, so then we end up just having to combine this. So this is one scenario where it's nice to have them just combined together, right? Because there's simplification. 0 to 2, 4x minus 2x squared dx. Okay, antiderivative time. This is equal to 2x squared, add 1, divide, minus, add 1, divide, 2/3 x cubed from 0 to 2. Okay, now plug the 2 in. That's going to be 2 times 4 is 8 minus, and then you're going to do 2 in here. I'm going to get an 8 here, 16 over 3. Okay, I'm going to do minus, plug 0 in, but look, these are x's, so I plug 0 in, I'm just going to get a big 0. 8 minus 16 thirds, which we could plug into the calculator, or we could combine into one fraction, which actually would not be that hard to do, right? So 3 times 8 is 24, so this is just 8 thirds. So hopefully that's not too bad to mess around with. Let's see what's going on. All right, so what else can happen? Well, one of the other big things that can happen, which again, this is very important for us when we're going to do volumes later to have this in our head, is we can have two curves here that are not actually functions of y as a function of x, but could be represented as x as a function of y. So this picture here, these both do not pass the vertical line test, so there's no way for me to go y equals some x's. This vertical line test says you can't do that. But I can think of these as both as x is a function of y. If you kind of just like tilt your head, hopefully you can see the picture that we had above with x's, right? It's the same idea. Okay, so then what kind of becomes difficult here? Well, you have to just kind of orient yourself correctly, right? So you got to remind yourself that, you know, this is the positive y direction, and so this is positive y. So we're always going this way, right? So before, when you had a to b, a was always the smaller number, smaller bound, and then you went up to b. So how does that work here? Well, c will be the smaller bound, so down here, up to d. Okay, sometimes you'll see that, like mentioned here, instead of, you know, like a to b, left to right boundary, it's as weird. You'll see c here, the smaller number, is the right boundary. Again, tilt your head to the right. You'll see this is the right boundary and this is the left boundary. Or you could think of it as like top and bottom. That's fine too. But we're going to be integrating from c to d here. So when you set this picture up, okay? And then, so what we need to be able to do then is think about, okay, what curve minus what curve? Well, again, this is the positive direction in x, right? So this curve is on top of this curve, right? Because it's got more positive or larger x values, I should say. So the curve more to the right, if you're looking this way, if you haven't tilted your head, right, and you're just going, okay, left, right here, this curve more to the right is the top one. All right, so top, bottom, C to D. But once you've kind of oriented yourself like that, it's not too bad to do this. So let's just jump into an example to kind of see what we're going to do here. So let's try this out. Right away, looking at this problem, I see x is a function of y, x is a function of y, so okay, I know I need to do this new method. All right, and then I also see no bounds. So my first step here is let's find the bounds. Okay, so that's going to be when these two are equal, aka 2y squared equals 4 plus y squared. Move this over, you're going to end up with y squared equals 4, which means y is plus or minus 2. Okay, so go find 2, boom, go find negative 2, boom. All right, there they are. So those are our bounds, okay? So 2, negative 2. That's our C and that's our D. So we're going to be integrating from negative 2 to 2, okay? And now what we need is which function's on top, which is on bottom. So again, if you tilt your head, you could see this one's top and this one is bottom. Or if you'd rather just remember for these situations, it's always right minus left, you can do that too. So you just kind of have to think about these curves a little bit. you could just kind of do this by looking at the functions. This one is the parabola that's been pushed up for at the start. So this parabola starts down here at 0. This one's been pushed up for. So, okay, this one's going to be the one that's on top, aka the right bound. So that's 4 plus y squared minus 2y squared dy. So, okay, that one's not too bad to do, right? So that's going to be the integral -2 to 2. Let's do some combination here. 4 minus y squared dy. Okay, so that's going to be 4y minus 1/3 y cubed. Add, divide. All right, we're going to do that from -2 to 2. So let's plug in the 2. We get 4 times 2 minus 1/3 times 8 minus, okay, now let's plug in -2. 4 times -2 minus 1/3 times -2 cubed. Okay, so that's 8 minus 8/3 minus, and then we've got another negative here, right? So that becomes a positive 8 minus minus, but another minus, right? Because it's an odd power, so that minus stays. So 1, 2, 3 minuses, minus 8/3, okay, which ends up being, so we've got the 16 minus 16/3, and then from there you can, put this in a calculator, do some fraction work, but that's fine too. Okay, so one thing I just want to point out, and it's not necessarily super useful, but maybe it would be nice for you, is we ended up at this point with the same thing for each of these, right? When we plugged in 2 and -2, which you might have seen as weird. But it's not weird because there's symmetry here. Specifically, there's symmetry about 0. So you should always be looking for stuff like this. When we're looking for this area, the total area between these two, really we could have just done half of this and doubled it, right? Because this area over here is the same exact one as this area because of the symmetry. So just as a thing that you could be thinking about, this integral is really equal to 2 times the integral from 0 to 2, or -2 to 0, whichever you prefer, of, and then just to have it simplified, this. So just keep that in mind. That could be a helpful thing sometimes, to see the symmetry and change some things up. Plugging in 0 is nicer than plugging in -2, so it would have made things easier here. Okay, so do a bunch of practice. Practice drawing out these pictures. You can use Mathematica to help, but it is good practice to do it by hand too, to recognize functions, find your bounds, figure out what's on top, what's on bottom, do the antiderivative, plug in, see what you get. Any questions, let me know, and I'll see you in the next video.